So we're going to keep talking about Chapter 3, relationships between quantitative variables. And we talked a lot the first day of this lesson about positive associations and negative associations and no association. So positive association means both variables go up together. Negative means as one goes up, the other goes down, right? And no association, the dots are just all scattered and looks like there's no pattern whatsoever. So today we're going to describe patterns with something called the regression line. So here's an example. The question might be, how much does weight increase? How much does weight increase, say on average, as height increases? My sisters like to say, oh, Beth, you're thinner than I am because you're taller, and you weigh 20 pounds more than we do. I'm like, yeah, pretty sure the 2 inches in height difference is not 20 pounds, kids. So does that make sense? Like, how much on average, if you're 1 inch taller than somebody else, how much more do you expect to weigh? And some people more, some people less, but on average, what's the difference? Okay, and by that definition, my sisters are definitely thinner than I am, but they refuse to believe it. So regression analysis, so this is the area of statistics used to talk about this kind of stuff. So the area of statistics used to examine the relationship between a quantitative response variable and one or more explanatory variables. In this class, we're just going to handle the cases where you have one explanatory variable. But it is possible to use more than one. Like, for example, I could use your high school GPA, your ACT or SAT score, and and those two things to predict, like, your GPA in college. Does that make sense? I could also use one, but using two might be better than just using one of them. But using two of them is a class that's a higher level than this class. And you can do really, really cool stuff with this. So here's my one small story for the day, and I'm going to stick to the lesson for this. So Target used this to target new mothers. So they found that if you get new mothers into your store, they tend to stick to that one-stop shopping because it's easier for them once they have babies. I don't have babies, but I can imagine this is true. If I can go to Target and buy everything, I'll keep going to Target. So they were trying to figure out how could they predict that somebody was pregnant. And they found that based on like 3 or 4 things, they could predict with high probability that somebody actually was pregnant. And the great story is, and then they would send you ads with like pregnancy-related things in them, and then some other random stuff peppered in, like a lawnmower or something, so that it didn't seem too creepy. So the great story is what happened is there was this dad who came into a Target store irate because his daughter is getting these ads. He's like, my daughter is 15 years old. She's not pregnant. Why is she getting ads for, like, diapers and stuff? It makes no sense. And the manager's like, oh my gosh, I have no idea. I'll check it out, blah, blah, blah. He called the guy back a few weeks later just to say, oh my gosh, I'm so sorry again. And the dad says, well, I have to apologize because there were some things in my house that were happening that I didn't know about. And his daughter was actually pregnant. And he didn't know it, but Target did, with their regression equation. Isn't that nuts? So look up that story, because I bet the internet I think the New York Times wrote it up and did a much better job than I did. It's so terrible, but that's what regression analysis can do. I think Fred Meyers does this when they give you directed coupons, right? They take your purchases and they give you things that you might actually buy. So it's a great story. Okay, so the regression equation, back to more boring stuff, so sorry. This describes how, and the kicker is on average, the response variable is related to the explanatory variable. And the relationships we're going to talk about in this class are more or less linear, which means that the equations, the things look like lines. Does that make sense? This is something called a straight line relationship. So you look at this, and what you should always do to check and see if a linear relationship is plausible is look at a scatter plot of your data. So look at a scatter plot of the data. To see if linear is appropriate. Probably appropriate with height and weight, because as height goes up, weight tends to go up, right? But probably not, definitely not appropriate with stuff like length of day in Fairbanks, Alaska. That's going to cycle in a predictable way. Or average temperature in Fairbanks, Alaska will cycle as well, right? It won't be linear. Linear means like y equals mx plus b, straight line. And the regression line, this is the straight line. That, I'm going to say best in quotes, that best describes the linear relationship. So as close to as many points as possible. And there's a criteria that you use to determine which line is the quote-unquote best line, and we'll talk about that in a little bit. But for now, we're just going to look at some lines and talk about what these slopes and things mean in these contexts. But there's a way to determine one line that is the best line given a set of data. So you should use calculus to prove it is what it is, but there's a way to find a best. Okay, so what is the equation of a straight line with slope m and y-intercept b? If I say line, you guys say y equals?
mx plus b.
Mx plus b, exactly. Okay. When you talk about equations for regression lines, so y equals mx plus b is like the perfect regression line. If you had all the data in the world from the whole population, that is what you would get. But you can't, usually you don't take censuses to do studies, right? Like that's just too much work and too expensive, yes? So what you do is you take a sample, and when you're talking about a regression line, the statisticians use y hat equals mx plus b. So that little symbol is read y hat. And we're talking about a regression line that's been collected from some data. Oh, math people and their symbols. Your book actually ends up using the words for the variables, as in like if y means height and x is weight, it will say height, and then it will say weight for x. Sometimes it might not be that nice, okay?
So it will say like height.
It'll say height equals m times weight. Yep, so it's totally obvious what variable's what, but I might not be that nice, and I might use x's and y's, like what they stand for. Okay, so here's the height and weight example. So here's a regression equation for the relationship between the weight in pounds and the height in inches for men aged 18 to 29. So estimate the average weight for men in this age group who are 70 inches tall. So what comes out from y is the weight. What goes in for x is the height. So how would you figure out the average weight of somebody who's 70 inches tall?
670 minus 250.
Yep. So y hat would be 6 times 70 minus 250. And of course you get calculators, but that's 420 minus 250 or 170, right? Okay, let's just label it, it's pounds. So on average, men who are 70 inches tall weigh 170 pounds. It doesn't mean every 70-inch tall person weighs that much. It just means the average weight for that height is this. There will be some variability. That's 70 inches is...
6 feet.
Yeah. I don't know if that's accurate or not. I got it out of a textbook, so I have no idea.
6 feet.
Hmm?
It's just shy of 6 feet.
Yeah, so probably reasonable.
5'10".
Yeah. Okay. What is the slope, and what does it mean? So, first of all, let's handle the first question. What is the slope? M is equal to 6. And then think back to like Algebra 1 and think about how you found slope. How did you find slope in Algebra 1? What did you use? Rise over run. And what variable was the rise, x's or y's? Change in y over change in x, exactly. Change in y over change in x. And this will help you find the units of the slope. So what are y's units? Weight, so its units are pounds. And what are x's units?
Inches.
Inches. So m is 6 pounds per inch. Does that make sense? So in a semi sort of sentence, this means that if height goes up by 1 inch, that's the response, the, what's the other one called? The explanatory variable, right? If height goes up by 1 inch, what happens to weights? Yep, weights go up by 6 pounds on average, right? Not all for all people, but on average, that's what happens. So that's the slope, and that's what it means. Okay. Does that make sense? All right. And also one thing just to note is that this equation was made for men, so the weight difference probably is different for women because we have less muscle on average. Does that make sense? Mm-hmm. Okay. Here's another one. So a study was done in which researchers measured the maximum distance at which an automobile driver could read a highway sign. There were 30 people that did this, and this is the regression line, 577 minus 3x. This describes how the maximum sign legibility distance is related to driver age. So notice that the slope of this thing is a negative number, yes? Does it make sense that these, as age increases, the max distance you can see goes down? Yeah, okay. So what is the slope and what does it mean? So the slope is equal to negative 3, and that's delta y over delta x, or that delta symbol means change in case you haven't seen that before. So what are y's units?
Sign legibility distance.
Yep, so distance, I don't know if I told you that it was measured in feet, but I think did I say that?
No.
Okay, it's supposed to be in feet, so sorry. Over x's units are age. In years, yep.
In centuries.
In centuries. That would be a very large unit of measurement. Okay, so for every year older a participant is, or you can say, or for a 1 year increase in age, what happens to the max distance? The max sign legibility distance decreases 3 feet. On average. I should always add that, on average. Some people might, have better eyes and they're their distance that they can see does not decrease as much. But for the average person, that's what happens.
It doesn't tell us about when that was still, like, who their whole group was.
No, but I mean, if this was a paper or something, that might tell you who their group was. Yeah, they didn't. Well, I think the point was they didn't tell you the ages of the participants. Does that make sense? So it didn't tell you, and I assume it's probably actual drivers. So let's say 18 to 70 or something like that. Who knows? So let's predict the sign legibility distance for people aged 30, 60, and 90. So y hat, I'm going to put a little parenthesis and 30, which means I'm plugging in 30 into that equation. So that's 577 minus 3 times 30. So I want you to do that and tell me what you get. It's actually not that hard with a calculator. It's 577 minus 90. 487, exactly. Y hat for 60-year-olds would be 577 minus 3 times 60. So 577 minus 180, so that's how much? 397? 100 less feet. Holy moly. I want to be 60. Y hat of 90. Oh man, 577 minus 3 times 90, which is 270. Great. 577 minus 270 is 307, right? Okay. Does that make sense? Mm-hmm. Alrighty. No problem. Yep. Nope. If I'm being Speedy Gonzalez on caffeine, just tell me to stop. Okay, thank you. If someone can see 500 feet, about how old are they? How would you figure that out?
25.
How did you get it?
So I just took the extra 77 off the
Mm-hmm.
577 total feet and divided it by 3.
So what you're doing is you're plugging 500 in for y hat, basically, right? So 500 equals 577 minus 3x. Then just solve this equation. You go back in your Algebra 1 happy place, and you say, oh, I take away 577 from both sides, and I get negative 77 equals negative 3x. And x will equal 77 thirds, and get me an approximate decimal with 1 decimal place of accuracy. 25.7. Yep. Just so you know that on a quiz, if I specify you need to round to the nearest hundredth and you do it wrong, if I take off points. But if I don't specify what to do, then all manner of answers are totally acceptable. Just, you know. Okay. So, pretend there's a regression equation that relates average blood pressure, I'm going to skip that word on purpose, to age. And the average blood pressure of someone who's 20 is 120, and the people that are 60, it's 140. What is the slope of this regression line? So what I've done there is I've kind of given you 2 ordered pairs, and what you have to do is write them in the right order and then find the slope. So in your ordered pairs, who goes first, X or Y? X goes first, alphabetical. X, Y, Z. I won't sing the whole alphabet for you. So your first ordered pair is 20 and? Mm-hmm. And the other ordered pair is?
60.
Exactly. And the equation for slope, somebody said it earlier, was y2 minus y1 over x2 minus x1, right? Where those subscripts really stand for first and second. Like first y, first x, second x. And whatever's the first or second isn't really important, it's just that you're consistent with who's first and who's second. Yes?
It's 120 what and 140 what?
Oh, I don't remember what the units are supposed to be on blood pressure. I just can't remember what they are. Millimeters of mercury per something.
In
Or is this millimeters of mercury?
Yeah.
You know what? Google knows.
MHG, it's millimeters of mercury.
Millimeters of mercury. So yeah, it's something that I just don't understand what it, I know it means something with the gauge, but yeah. I mean, having a blood pressure of like 120 is reasonably good, right? Yeah, Hg is mercury, right? Yeah, I remember a bit from high school chemistry. So 140 minus 120 over 60 minus 20. So that's, 20 over, which reduces to almost.
Oh,
One half.
sorry.
It's okay, it's okay. Yep, it happens. Okay. And so that you would have units, millimeters of mercury per year. Is that, assuming millimeters of mercury is the proper units for blood pressure? Okay.
Would you want us to write it like a fraction, or can we put 0.5?
Oh, vote 0.5 is totally fine. It's equivalent and not wrong. Either way is fine. So it means as your age goes up by 1 year, your blood pressure goes up by a half of a unit. Does that make sense? Or if your age goes up 2 years, your blood pressure goes up by 1 unit, right? Okay. Oh, question B. What is the estimated systolic blood pressure for people who are 70? So for that, I need the regression equation. I only have the slope, right? So you're like, okay, well, y equals mx plus b, y equals 1/2 x plus b. Did you learn at some point in time in your lives that you can then plug this point in for x and y and find the b? Okay, let's do that. And either point will give the same b. So if you don't like that point, pick the other one and confirm we get the same thing. So that would be 120 equals 1/2 times 20 plus b. So 120 equals 10 plus b. What's my b going to equal?
110.
B is equal to 110. So my regression equation, y hat, is 1/2 x plus 110. And that will predict the average blood pressure for people who are set for any age, x. So how would you do 70-year-olds? Plug in 70 for x. Very good. So y hat of 70 is 1/2 times 70 plus 110, which I think is 145. Is it mg/hd? Or millimeter? Millimeters, yeah. I obviously need to learn my stuff. Okay. And does it make sense that on average, as age increases, blood pressure for most people tends to increase? Unless they have like a life event and they have a health, they change their health habits and stuff, right? Okay. Now, obviously this regression line is not going to describe everybody perfectly. Everyone's going to be a little bit different. Yeah?
For getting that b equals 110, if you were to put in the 140 and the 60, would that still came out the same?
Yeah, definitely. You would have had 140 equaled 30 plus b. Does that make sense when you plug them in? Yeah, so it doesn't matter which point you use, it will be consistent, and it's not the same if you made a mistake. Yep. Okay, so what was I saying? So I was saying that not perfect for everybody, and so you want a way to think. You want a way to describe how much an individual varies from the average. Does that idea make sense? Like, am I above average, below average? How am I average? Am I special? How? And that thing is called the prediction error. So this is the difference between the observed y value like from an individual person, subject, thing in your study, and the predicted value. It's written as y minus y hat. So think about that blood pressure for a second. If your blood pressure is higher than average, this value is going to be positive. Does that make sense? Because then y will be bigger than the average y hat. If your blood pressure is lower than average, this will be negative. So let's write that down. If y is above average, this is positive. If y is below average, this is negative. Residual equals prediction error. It's just a synonym. Okay? And it's the word that statisticians are going to use. I think it's just because it's shorter. So it's called a residual, y minus y hat. That's what a residual is. So same thing. Just they had to give it fancy words. And so the point is you can use this, you have all this data and use this data to get this regression line, and then you can compare the values that you had to things you predict using said regression line and see how much they're off by. So we'll find a few of those next. So here's this regression line. So same thing. This is the equation for the max distance and the max distance and the age. So to find y minus y hat, we have to know what y is. Thanks. We have to know what y hat is as well. So y is the actual value that you're given. So you have an actual 18-year-old who can see an actual distance of 510 feet. So that is your y. How would you find the predicted value that the regression equation gives you? What do you plug in? 18. Very good. So y hat will be 577 minus 3 times 18. That should come out to be 523. And so then y minus y hat is 510 minus 523, or negative 13. Very good. Yes?
Is there a symbol for the residual?
Not that I know of. So in the class I took last semester, they just said resid. So I don't know if, and R means something else. So definitely don't use R, okay? So I think you should just go with y minus y hat, or just write out, if you want to use resid, I don't care. Yes?
So he's obviously above average.
No.
But
He's below
wait,
average.
Okay, hold up, I'm reading it
It's
wrong.
okay.
I was confused because the description you gave us says that if it's above average, it'd be positive, and I thought.
But in this case, that would mean he can see farther than everybody else. Does that make sense?
Mm-hmm.
In this case, he can see less farther than everybody else.
Right, I didn't read the
This one right. Yeah, no, that's totally fine. Okay, so for a 20-year-old, you just plug in and find y hat, right? Let's just do one more because it's really pretty redundant. So y hat is 577 minus 3 times 20, which works out to be 517. Resid y minus y hat is 590 minus 517, or 73. So he can see from 73 feet further away than the average person, right? I think we can skip part C because you guys get the idea, right? Okay. So a question you might have is, oh my gosh, how the heck do they determine this best thing? Like, how do you figure out you've got all these data points kind of dancing around, and you're like, well, which line is the best? Is it something like this? Is it a line that would live like that? Like, how do you figure out which one is the best. Does that idea, this question make sense? And what statisticians use is something called the least squares estimation criterion. So here's what that says. The line for which the sum of the squared prediction errors for points in the observed data set is smaller than for any other line. So write that down and we'll talk about what it means. So for every single data point, you have the actual data point, and then you have the predicted value that's on the line. Does that make sense? And so the residuals, or the prediction errors, are going to be either positive or negative, but that is this little distance between those points. Got a data point and a point on the line, okay? So what you do is you take them, so you take y minus y hat. Why do you think you have to square them? Because some of them are going to be negative, and if you didn't square them, they'd cancel out. Does that make sense? And you're going to sum them all up for all possible lines. Lines, and then you're going to find the best one. And proving what line is the best one requires calculus. Like it was done in my Stat 401 class. It's not, if you know some calculus, it's not actually very hard, but the idea that you make this as small as possible. And one thing that squaring does is it also tends to overemphasize big differences and underemphasize small differences. Like 5 squared is 25, but 0.1 squared is a lot smaller, right? So you take this difference for all the different pairs and you find the minimum. And what pops out is, this. It's on your paper. You get this regression equation. Y hat is b1x plus b0. b1's your slope. b naught is the y-intercept, right? And this b1 is equal to, holy moly, big sum symbol, xi minus x bar, yi minus y bar over sum of xi minus x bar squared. I'm not going to make you use it. Let's just talk about what those things mean. So first of all, what are the bars? What's x bar? Mean of all the x's, right? What's y bar? Mean of all the y's. Mean of all the y's. This little sigma symbol means add them all up, right? So what you do is you take every single x, take away the mean. Every single y that you actually had, take away the mean. You multiply them all together. So you do for x1, like the first observation, first observed x minus x mean times first observed y minus y mean. You add them all up. You divide by, this thing is the residuals. See that? No, it's not residuals. It's some, no, I'm wrong. Not residuals. Take all the x's minus the x means, square them, add them all up. That gives you the slope in the equation, okay? And then the y-intercept is given by y bar minus b1 times x bar. That's what pops out if you know calculus, okay? I'm not going to make you use them. When I took Stat 401, we had to use them to find a few regression lines because we didn't know what the formulas were. But that's the basic idea. That's where it comes from. You're just going to use software. Are we given regression equations and have to interpret them, okay? But the point that's kind of cool is just from the data, you can figure out the best line using this formula. That's kind of neat. Without having to test every possible best line, which sounds like a terrible way to go, right? Okay. I didn't add that slide in. Okay, to the end. What we will do is we are going to find something called the sum of squared errors. And so this is the thing that we would want to minimize if we were doing that. So, and the symbol for that is SSE. And we're going to use that to compare these two lines and figure out which one of them is better for the given data. So the basic idea with sum of squared errors is you find all the residuals, square them, add them all up. So find all resids, square, and then add them. And that's probably the only context in which I would ask you to do anything with it, is to say, okay, here's a potential line, here's another potential line, which one is better by this criteria? Okay, that's all it's asking. So let's do line 1 over here. So first of all, you gotta find the y hats. So find y hat. So if x equals 1, what's y hat gonna be? 6. Does that make sense? Because you plug 1 in that equation? Okay. So we're off by 2 in that case. If x is 2, what's y hat gonna be?
9.
9. Great. Yep. 6 plus 3. If x is 3, y hat will be 12. Great. And if x is 4, y hat will be 15. Great. Then let's find the resids. So y minus y hat. So for the first predicted value, which y do I use with that? What's the observed value for that particular x? 4. You see that? When x is when we observed, y was 4, right? So the residual there would be 4 minus 6 or negative 2. How about the second value? What is the actual y value when x is 2? 10. So 10 minus 9 gives you 1. I think the next one is 14 minus 12, right? 2. And the last one is 16 minus 15, which is 1. And so the SSE for line 1 is equal to, take these numbers, square them, and add them up. So what's negative 2 squared? 4. 1 squared is?
1.
Plus 4 plus 1. For this line, SSE equals 10. Great. And then let's do line 2.
Sorry, can you go back? Where did that 4 plus 4 plus 4 plus 1 come from?
The SSE tends to take these errors and you square them and then sum them. So the 4 came from negative 2 squared. Good? Yep. And the reason you do that is because if you didn't square, you'd have positives and negative errors canceling out, and it would seem like you made no error when you actually have made a relatively large error. There's also a reason that the absolute value is not used. It's a bit technical, though, so we're not going to do that. So if x is 1, what's y hat in this case? 5. X is 2, y hat's going to be 9. Great. X is 3, y hat will be 13, is that what you said?
Yeah.
Yep, x is 4, and y hat will be 17? Okay, great. And then the resid, y minus y hat, will be 4 minus 5, right?
Yeah.
So negative 1. 10 minus 9, so 1. I think it's 14 minus 13, right?
Yeah.
So that's 1. And then 16 minus 17 is... So the SSE for line 2 is equal to 1 plus 1 plus 1, or 4. I know that's kind of tedious. But if I gave you 2 lines of how you compare which one is better than the other one. And so you want the one where the sum of squared errors is the smallest, because that means it's the closest. So which one of these lines is better?
Line 2.
Line 2, yep. So that's what the answer is for part B. By the least squares criterion, which of the 2 lines is better, and why? And the why is because the SSE is lower. Smaller errors. Okay. So line 2. SSE is smaller. Okay. Good? All right. So now another thing we're going to talk about is how do you measure how strong a relationship is? And so this is why you can't use the letter R for residuals. So the strength of a relationship is called the correlation. So this is a number that indicates the strength and direction of a straight line relationship. Okay. And maybe you have or haven't heard this before, but some basic things. So correlation coefficients are always between the numbers of -1 and 1. And they can also be those numbers. Like it's possible to be -1 or be +1. That's possible. Now, the magnitude of the correlation indicates the strength, which tells you how close the points fall to a straight line. So if those points fall tightly together, that will be closer to either +1 or -1 if it's a positive correlation or a negative correlation. So positive correlation means positive slope, negative correlation means negative slope. A correlation of either 1 or -1 means that there is a perfect linear relationship, i.e. those dots fall in exactly a line. Think that happens very often in real life? Probably not, right? Most times there's going to be some variability around that. It's going to be like, line-ish. Yes, and then you, okay?
If you wanted to skew your survey, couldn't you make the numbers for your X and Y lines huge compared to your actual data?
Correlation coefficient doesn't depend on the sizes of the labels of the axes at all.
So what I meant was then wouldn't the dots fall closer into a perfect line?
This won't be affected by that. If you manipulate your axes of your X and Y axis to make it look better, it won't affect this value.
Okay.
I think what you're saying is that you can manipulate the data some to make it look like it's better than it actually is, or make it look worse than it actually is, right? Yeah, and this will not be affected by that. That's just misleading statistics. Yes?
I was just going to ask a much simpler question.
Okay.
So if your lines are perfect positively, or let's say negatively, like every year you got older, every 1 year you got older, your vision went down 1 foot, that would be like perfect.
Yep. And it doesn't matter if it's that negative line or if the negative line has like a lot less steep slope. What matters is that they fall in a perfect line. Yep. And then the sign of the correlation indicates the direction of the relationship. A positive correlation means that they tend to go up together. or they tend to increase together. And a negative correlation indicates that when one goes up, like age goes up, max sign legibility goes down. Likely to down. I probably meant to say decrease, because I do actually English sometimes. And a correlation of 0 means that the best straight line through stuff is horizontal, and this is no relationship. Like, for example, height and GPA, probably not a relationship between those two things. Unless we look at, maybe men and women introduce some kind of subgroups there that make it possible, but in general, probably not. Okay, so which of these numbers could not be values of a correlation coefficient? Why or why not? Negative 1.7 and 2.5. And the reason is that correlation coefficients are between plus minus 1. So negative 1.7 is too low, 2.5 is too high. Okay. And the reason you can't use R for residual is R is the letter for correlation coefficient. So that's just, there's probably a reason that I don't know why it's always R, but it is R.
No.
Might come from the fact it's like regression analysis, so R for regression. I think that's probably where it comes from. So for each pair, tell me whether it's likely to have a positive correlation, a negative correlation, or none. So hours of TV watched per day and GPA. So as hours of TV watched goes up, what probably happens to your GPA?
Goes down.
Goes down. So this will be negative. Yes. As hours watched goes up. Or if you're somebody who just needs background noise to work. I mean, like, I'm one of those people. I need to, like, have Doctor Who playing in the background to, like, grade the quizzes I have to grade. It's just, you know, how I operate. Otherwise, it feels, like, too painful because I'm a weekend working. Number of liquor stores and number of ministers in the Pennsylvania cities. Now, this is not what you expect. It's not what I expected either. So, what do you think? My first guess would have been nothing, okay? Positive, yeah. So those of you that said positive, why do you say positive?
Trying to increase the preaching as the stores are selling more.
Yeah, so we're bringing in more preachers to help those poor people who are drinking too much. That would be not what I would say as the reason. The reason that I would say is that if the number of liquor stores goes up and the ministers may also go up, because it might be the case that you've got a big city. Does that make sense? So it might be the big city variables in there sort of confounding things a little bit.
Also, liquor stores and churches are both in poor neighborhoods.
Yeah, so, but it's not even that. I think it's just that,
But like, I don't know.
yeah, it's completely possible. There might be more than one explanation, but my explanation might be that big cities have lots of both, right?
Is that another one of those that you can just argue?
Probably, right? Like you can give me some kind of, it's a bit of a tricky one. So yes, you could try to argue, but I think it's pretty sure it's going to be positive, right? And it would also be different in different countries. Like, say, Sweden is really secular. It's like one church per town. I mean, I don't know if it would relate there at all. So it's not clear. But I think the city sizes kind of means that those two things are going to increase together. Performance on a strength test and age. Negative. Your performance in the strength test tends to go down as you get older.
Could you also say negative association rather than
Yeah.
correlation?
Well, the question did ask about correlation, so we probably should ask what the question said. But the negative association, negative correlation are going to be the same in the sense that they're either both negative or both positive. So performance goes down as age goes up. Okay. So R is the letter used to represent the correlation coefficient. So I think I told you, it's a little bit mathematical notation, that R is between +1 and -1, right? If that's true, what is the squared thing in between? If your R's are between -1 and +1, and then you take those values and you square them, what are the things that come out? It's got to be positive. And what's the lowest it can be? 0. Does that make sense?
Yeah.
Okay. If R is between -1 and 1, if you take those values and you square them all, the lowest thing you can get is 0. The highest thing you can get is +1. Okay? And I think on your paper I wrote lots of letters. I wrote this thing equals, did I say SSTO minus SSE over SSTO?
Yeah.
Okay, yeah. You don't have to know this, but I just want to tell you what those things stand for in case you see them in a future class. So SSTO, this means sum of squares total. You can see where they got the SS and the TO from, right? It's sum squares total.
Yeah.
And this is sum symbol, y sub I minus y bar squared. So where y sub i's are all the observed y's minus all the means squared. This is called the total variation in y. So y could be heights. It's the total variation you have from the mean you have in heights. SSE, we actually already saw, right? Sum of squared errors, right? So that is the sum of y sub I minus y hat, y sub I hat, or y hat squared. This is the sum of square errors. And here's what R squared tells you. R squared tells us the proportion of variability of y explained by knowing x. This is the part you got to know. So, for example, you might say, okay, well, how much of the variability in height is explained by shoe size, for example? Does that make sense? Like, big shoes tend to also mean tall people, right? But how good of a predictor is that? So, here's a few examples. So the correlation between height and stretched right handspan is 0.74. So to find R squared, you take 0.74 and you square it, and you get about 0.55. So this means that height explains how much of the variation among observed right handspan? 55%. And one way you can get a higher R squared value, like in a different class that you were taking, is you could add in more variables. You could say, okay, I'm going to use handspan, and I'm also going to use foot size, for example. Maybe that will explain more. But this was kind of weak. The correlation between television watching and age is just 0.136. R squared is about 0.0185, so age explains what percent of the variation in amount of television watched?
1.9.
1.8, yeah, let's just use the decimals they gave us, but 1.85%, right? So not very much. And that tells you that, well, age is no, was it? Yeah, so it tells you that's a crappy relationship. Don't bother using that one. Okay. Now, there's a little bit of information lost when you square R. What do you lose from the number when you square it? If it's positive or negative, does that make sense? So suppose, the regression line is this, and the value for R squared is this. So that means that R squared is 0.9, yes? So how could you find R from that? Take the square root. It's not 0.3. You can think about that as 9/10 rooted, and it's going to be 3 over root 10. But as a decimal, R is about equal to 0.949 approximately. And the question is, well, technically speaking, I made a slight mistake. I probably should have said plus or minus, plus or minus, plus or minus. And the question is, which one? And I gave you the information that you need to figure that out. That's the regression equation, right? The slope is negative. Therefore, there is a negative association, right? Therefore, R is negative 0.949.